If there's only one driving force, which can be the temperature gradient or the electrical potential gradient or the chemical potential gradient, to drive this kinetics flow process, then we can use this beautiful equation to calculate or estimate the entropy production rate per volume by using what? By measuring the corresponding driving force, can be heat flow, charge flow, or atomic flux times is corresponding driving force. And this is like the inner product. And this is just times. So it's quite easy. But however, if there are two or more driving force coexist or co-apply on this material systems, how how to deal with this? How to get the sigma dot? That'll be the question. So in the last section, which is more important part, we are going to introduce the coupling effect, which we can quantitatively express or show. We call it as a coupling coefficient. Then we are going to use like the Seebeck and Peltier effect to serve as examples to show you that under what kind of conditions you probably will have two driving force apply on your or in your material systems. Then the last one will be we call it Ansaka symmetry. This is some kind of mathematic trick, something we are going to use in this part. So let's move to the coupling coefficient and coupling effect between the forces and the flux. But before we address this one, we want to move back to the entropy production. Because if there are two driving force, then the entropy production for sure will difference. So let's move back to how entropy produce inside your materials. So based on the second law in thermodynamics and also in macro scale, we can say that the entropy change of the system equals to the heat change divided by temperature. But this is under thermodynamics, which means that this is reversible process. And furthermore, entropy also can be like rewritten or expressed equals to the Boltzmann constants times the log omega. Omega is the total numbers of combination of all the atoms, different kinds of atoms. So the entropy is some kind of measurement of the numbers of states, which means that the combinations with significant probabilities of being occupied. So this is in micro scale because we talk more about how the atoms arrangement, so the numbers of possible combinations. So if you combine all this, probably you can like have some idea. If we talk about the change of entropy in your interesting cells is like the cubic, you are interesting cubic, something like that, then we can have this kind of relationship is the entropy change equals to what? The entropy change inside this box, inside this cell, can be equals to the entropy produced by itself, and the entropy come from surrounding cells. So we use a flux because possible some people will give you some entropy, something like that. So the total entropy change in a cell can be simply can come from either you generate the entropy or some entropies come from surrounding cells. So based on this idea, if you recheck the thermodynamic equilibrium state and also the steady flow process we discussed in prior sections, as we know, the state function does not change with time for both cases. State function, but actually, as you remember, entropy is a state function, right? So this also means that the entropy change rate equals to the entropy change equals to 0, right? But it's a little bit weird, right? For thermodynamic equilibrium state, the total entropy change or change rate equals to 0 probably it makes sense to you. So but let's also tell you that we don't this cell, this box does not produce any entropy, and it also did not get any entropies from surroundings. But for steady state flow process, we also have ds equals to 0. But how about, does the cell produce entropy? What's your opinion? We spend lots of time introduce the sigma dot, right? It is a rate of entropy production, so per volume. So yes, this cell produce the entropy. This is positive, but this is 0. So which means that the entropy flux is negative, which means that this box does produce entropy, but also the this flux, I mean this entropy flow outside this box. So the total entropy change rate or total entropy change still equals to 0. So this is quite important. So sigma dot actually is put more efforts to actually to put, I mean, sigma dot actually is just this term. So following like slides we introduce, I mean, the sigma dot we always ask you about actually is this term, not the total system. Otherwise, the state function does not change with time, which means that the total system, if you combine everything, the ds should be equals to 0.所以在这里的话，就是蛮重要，是说我们在前面在定义的时候，其实有讲到说，不管是热平衡状态、热力学平衡状态，或者是 steady state 的 flow process，我的状态函数事实上是不随时间而改变的。但其实在热力学那个时候有讲到说，其实熵就是一种状态函数。但如果按照这个逻辑来讲的话，这两个应该它的状态函数都不随时间改变，所以照理讲，它们的 S 都不应该它们的熵都不应该有改变。那这时候事实上就会有点跟刚刚你学的前几个 slide 学的有点不太一样，因为前几个 slide 我们花蛮多时间在介绍heat flow、mass transport 或者是charge flow，它会产生 entropy。在它产生 entropy 的情况之下，为什么它的 ds 又会等于0呢？所以在这里课本就，我们的课堂就花了一页跟大家说，对，它会这个系统它 produce entropy，然后我们也花很多时间用这个来衡量哪个动力学，哪一个系统的kinetic process 是比较快或比较慢的，但它其实不违背这整个 idea，因为我们只问这一项，但就整个系统来讲，它还是等于0的。那另外一项就是 flux 的部分，就是 entropy 的 flux，就是跟就是附近的这个环境交流的这个 entropy 的 flux，事实上是它产生了 entropy，但它 finally 还会给附近的 surrounding，所以整个系统 total 加起来还是等于0的。但这跟 equilibrium state 是非常不一样的地方，在 equilibrium state 的话，它自己本身其实没有产生 entropy，那还跟附近的伙伴环境其实也没有entropy 的交流。Okay, so let's move forward. So just remember that for steady state flow process, the entropy production and also the flux not equals to 0. Okay, so let's try to like because we are going to have like a two or more driving force, right? So I'm starting from entropy production, try to derive how can we deal with this kind of situation to get the sigma dot when we have a two or more driving force acting on our materials. So we starting from we call the entropy um, mass. We have a mass conservation law, right? This is some kind of entropy change of the system. Like come some kind of like entropy conservation, something like that, because the total entropy change of your interesting cell equals to either the system produce the entropy or it's the flux coming from or interact with surroundings. This is what we learned from previous slide. But the unit here is we have divided by the volume. So this will be the entropy change per volume. Then I try to get the sigma dot. So I need to divide it with time together. So I got the total entropy change rate of this cell or this cubic. And the production, when I divide it by time, so I'm going to have the rate of entropy production per volume sigma dot. And this one, we have the flux, entropy flux, the change in entropy flux, which means that the interaction with the surrounding cells. And how about if I divide it with time? And what would be? Then it will be equals to negative uh, entropy flux. We take the gradient of the entropy flux. Why you can have less to here? So I give you the other example that'll be more like you have some idea here. This is the continuity equation for the mass transport. So we have a concentration change rate can be expressed in the negative of a gradient of the flux. Okay, so if you change concentration to be as entropy, then the flux here can be the entropy flux. Then you divide it with time, right? So it will be identical with this term and equals to negative divergence or gradient of entropy flux. Okay, and if you forget the gradient, actually it's just you partial with the different like length along different coordinate and sum them together. Okay, so this is what we have here. So we already have a sigma dot, so just like arrange it. So this we call a continuity equation of entropy because this is a total entropy change rate equals to the production rate and also the interaction with surrounding, which means talking about with the interaction, the flux, I mean entropy flux interaction with the surrounding cells. So it's a negative flux of entropy, and we take the gradient on the flux of entropy. Then we just move let's turn to, or we just move let's turn to a left-handed side. So we have this equation. We have less sigma dot and entropy production rate per volume equals to this plus this. Okay. Then we already have a sigma dot, right? So then we need to do some mathematical calculation and combine with thermodynamics. And the detail deviation are shown in lecture note, page 6 to 7, so you can check them. But I just write down the summary after the long, like 1 or 2 pages deviation. We can get the temperature times the sigma dot equals to like this. This is the heat flux times the negative temperature gradient divided by T. Actually, this is F capital Q, right? And plus the summation term and I can be 1, 2, 3, 4, 5, right? The flux dot, this is the negative potential gradient. So if you have different type of kinds of potential, then you just sum them to sum them together. So as long as you have this, you can just summary them as equals to summation flux times flux I times the force I or dot force I. That'll be better. This is a interproduct. Why? Because this is a flux and this is a F capital Q. So also I can put this inside them, so I can just simplify this equation as summation of flux times the or dot with the force. So if you rewritten it, can be summation alpha, J alpha. I use J to represent the flux. Force is F alpha. So this is more easy or simple equation we have, right? So as long as you have two or more driving force, and in order to know the sigma dot for resistance, then you just sum them together, then you can get a sigma dot. In order to something like uh, make you have more ideas, so I give you an example here. If I have a metal bar and there are two driving force, temperature gradient F capital Q and electrical potential gradient F small q, applying on this metal bar, what is the sigma dot? So we do have two driving force, right? So based on this equation, this relationship, we will write down like T sigma dot equals to J F capital Q, capital Q, F capital Q, J dot F capital Q, and also we have the other driving force J small q, F small q. This will be, so how, as long as we put this back, then we can get a sigma dot. It's quite easy, right? And do you know the F small q and F capital Q? Yes, right? Because the temperature gradient is you ended or acting on these materials, and the electrical potential gradient, for sure you know that because you equip or you put in these systems. So now the point will be, what's the current density and also the heat flux? Now, this is the most important part, is regarding to the flux term. It's not just that easy, because based on the detailed deviation show that the flux of alpha entity equals to summation beta L alpha beta F beta, which means, what this means, if you try to do one thing, you use alpha to represent beta, so you will have L alpha alpha F alpha plus beta can be beta, L alpha beta, F beta. So which means that, what this means, the alpha flux not only driven by F alpha driving force, also can be driven by F beta. So when I try to write them together, which can be shown like this: alpha flux directly driven by alpha driving force for sure, but also need to consider F beta also contributes some flux in alpha flux, and the quantity contribute how much will be depending on the value or magnitude of L alpha beta. So you can directly written by this, and this is some kind of linear relationship or linearization approximation. So we will derive this in like somewhere in the like in next slide. Sorry. But try to use like explain this we call the coupling between the force and the flux is when beta field driving force F beta induce a partial flux of alpha quantities through the coupling coefficient L alpha beta. So this is we call a coupling coefficient. So the alpha flux for sure were directly driven by F alpha, but also coupling effect with F beta, and how much the contribution it will be depending on the magnitude of this alpha beta. So if you put this idea back to here, we know that because there are two driving force, so this is J small q, the current density is not, it is, because we do have the temperature gradient F capital Q. F capital Q temperature gradient also contributes some quantities in current density. The same idea would be like a heat flow. Heat flow or heat flux is directly driven by temperature gradient for sure, but the heat flow now also the electrical potential gradient also contribute some heat flow. So in order to know the current density and also the heat flow, based on this flux force relationship, we can express like this. Heat flux directly driven by F capital Q, and we can write down on your right-handed side is driving force contribute on flux. So we write down as equals to L capital Q. And because inside the system we do have F small q, F small q, which means that F small q also contribute on heat flux. So the coefficient we call the right-handed side is driving force contribute on heat flux. So we have capital Q here. So as long as you sum this together and you can get the total heat flux passing through this metal bar. The same idea about the current density, directly driven by the electrical potential gradient, and the coefficient is the small q, F small q contribute on JQ, so we have the L small q, and also because we have the F capital Q contribute on current density, so we have L small q capital Q. So based on this like ideal, you know the coefficient part actually right-handed side, which means the which driving force and contribute on which flux. So this is how they name it. They call them. Okay, so as long as you know this, you sum them together, then you can get the current density. Then put them to get inside this equation. So I can get the sigma dot. So this is we call a coupling between the forces and flux. As long as how we use this, under what kind of conditions we need to do this. As long as the driving force, we have two or more driving force, and the other, and we have a coupling effect from other driving force acting on the other like flux. Okay, not the direct one, but also the coupling effect. In most of cases, the coupling effect is not that small, but as long as you need to calculate, so you know how large or how small it is, you need to consider it or not. But based on the theory, starting from entropy production, you need to, as long as you have two or more driving force, you need to use this equation to get the sigma dot. And for sure, yeah, this equation also work for you only have one driving force, right? Because you only have one driving force, so it's not necessary to have this term. You just have one term, right? Okay. Okay. So next, I'm going to show you why the 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 coupling coefficient, which means the flux force relationship, is shown in like linearization approximation. So next slide is going to show you why. So I just copy the equation we just showed you in previous slide. And the flux of specific quantity can be driven by the various form of driving force. This is important. So what this means? This means that the heat flux, give you an example, the heat flux. The heat flux is influenced, is changed by various driving force. Can be the temperature gradient, electrical potential gradient, and so on. Interfacial potential difference, something like that. And therefore, this is it is a function of those driving force can be written as this, and we do have the corresponding different type or kinds of driving force. Then if you try to expand the heat flux with respect to different like a driving force to the first order in Taylor's series near the equilibrium point. What this means? Do you remember what is the Taylor's series? 泰勒展开式. Then Taylor's series tell you that the function f of x equals to f at x0 plus f prime x0 x minus x0. This is a Taylor series. And we just replace the f this function as heat flux, and the x replace as heat flux. This is a driving force F capital Q, and F replaced by the heat flux, and X replaced by the F capital Q. Then I just try to like rewritten these equations, show like this. And in order to simplify these results, we assume that near the equilibrium point, which means that all the driving force are very, very small, close to zero. So under this situation, this will be zero, this will be zero. F0 is zero. So under these situations, this is zero as well. So when I try to rewritten these equations, will be the heat flux can be written as the heat flux prime times the F capital Q. The prime means the partial with what? F, right? So you can write down as this. Heat flux can be written as prime means respect with partial with FQ. And probably we do have other driving forces, so we partial with F small q, and so on. So the heat flux is a summation of all this. If you compare this one with the general flux force equation you just derived, you compare this with this, you will find that this L, this F, because as long as beta equals to Q, capital Q, then you find that alpha is, if alpha is capital Q, then this is capital Q, and beta is capital Q as well. So you find that this first term is L capital Q capital Q. It's F capital Q acting on the flux capital Q. And this term is if beta change to small q. So you have L capital Q small q. So this term, compare with this. This is the L capital Q small q, which means that F small q contribute on F capital Q, JQ, heat flux, and so on. So based on here, you know that Compare with this, you know that what is the coupling coefficient or direct or coupling coefficient. Based on this definition, we know that the L capital Q, which means that when you acting 1 unit of F capital Q, the contribution, the change in heat flux, we call the L capital Q. And what's the L capital Q small q, which means that when you ended or apply 1 unit of F small q, which is the electrical potential gradient, and the change in heat flux, we call it L capital Q small q. But if you think about this, when I apply 1 unit of F capital Q, actually is equals to when you given the same temperature gradient, also at same working temperature, environment temperature, the heat flow, the change in heat flux. Based on this, you know this L capital Q is related with material property, because even for different materials, even you apply you put you for different materials, if you apply the same temperature gradient and put in same environment, that won't lead the same heat flux, right? Depending on what? The heat flux will depending on thermal conductivity. So even though I haven't show you how to derive the real relationship, something like that, but you know that L capital Q actually is close or quite related with the material intrinsic material property. In this case, probably were related with thermal conductivity kappa. And L capital Q small q, which is different like a driving force to acting on the heat flux. This people call it as a coupling coefficient. This the same, right? The same, so we call it direct coefficient. For this, when you apply connect to the same battery, you have different materials, but connect to with the same battery, they won't lead the same. The change in heat flux will be for sure will be different depending on your materials, right? So L capital Q small q also is related with like intrinsic material properties. So hope you now have some ideas. So now we already, first of all, we show that this equation really works. And also the flux here can be rewritten as the coefficient times this one, the driving force. So we just put everything together. So by using these beautiful equations, we can get the sigma dot. But in your textbook, they hope that they want to use the other approach to convince you this relationship really works by unit check. So I just copy the equations and let's do the unit check to see whether the units are the same or not. And let's take a look on your left-handed side. Is a temperature times a sigma dot. So for the temperature, the unit is K. The sigma dot actually is entropy production rate per volume. So the unit for entropy is a heat divided by temperature. So I did it this. So I got a joule cubic meter and second. So it's this unit. So let's check the other term. This term is a heat flux. Heat flux is a heat passing through unit area in unit time and divided by temperature. And this is temperature gradient. So its temperature gradient is divided by length. So delete this. So I also have the heat cubic time, the same. Heat cubic time. And let's check the second term. This is atomic flux is numbers of atom passing through per unit area and time. And this is potential, right? Potential is something like work divide. This is potential work divided by distance. So I also have the work. The unit for work is a joule and cubic time. The last one is a flux. The flux is an numbers of entity passing through a specific area during unit time, and a force actually is a force. And in order to have energy, so I times the delta x together. So the upper, I have the force times the distance, which is the energy. So it can be a joule and also a cubic time. So after unit check, this equation works. Okay, so you can like use this after unit check. Then I'm going to give you probably next question would be, Professor, so yes, you say that in order to get the sigma dot, as long as you know the flux and force. So can you give us how to get the flux and force? So I give you some examples, and actually these three examples show in previous slide. For the the heat flux times the driving force is a negative temperature gradient divided by T, right? And for the heat flux here, in order to get the heat flux, you can use a Fourier law equals to negative thermal conductivity times the temperature gradient. You can put this here. Then you can have a flux times the driving force. And the mass is atomic flux times the driving force is a negative chemical potential gradient. So the atomic flux can be get from the fixed first law. Fixed law is a negative mobility concentration and also the driving force, which is a negative chemical potential gradient. You just substitute this term here, and you times this, you can have here. And if we talk about a charge, current density, or current passing through your materials, so for the flux here, probably people would use like the current density divided by the charge it carried. So there will be a particle flux density. And regarding to the force here, based on the equation, you know the force under the electrical field will be the charge times the negative electrical potential gradient, so it will be QE. This should like this one. But here we know we can divide the charge, right? So that's why if deal with the current or charge flow, the current we use the current density, and the driving force we use a negative electrical potential gradient. We did not use we did not put the charge Q here. So, and based on the current density, how can get the current density based on the Ohm's law? You can use like the negative electrical conductivity times the negative electrical potential gradient, or rho E. E is the electrical field. Okay. So now I hope you already have some idea about how to get the sigma dot as long as you have two or more driving force co-acting on these materials. Okay, so you need to write like this. You need to have the flux and force. And don't forget the flux need to modify, right? Because we do have the other secondary driving force to acting on your flux or contribute on your flux. So don't forget, you need to like write this like this. The case example we just show you, the current density not directly driven by electrical potential gradient. It also the the temperature gradient, F capital Q also contribute on the current density, and how large it is will be correlated with this coupling coefficient. Okay, so just for your reference, but we do have some examples in the following slides. So that's continue. When we mention about the new thing you haven't learned before, probably is we call a direct or coupling coefficient. So what is a direct? Which means that we have the same symbol here, right? The capital Q is F capital Q act contribute on JQ. So we have a same symbol. We call it direct because temperature gradient directly contribute on heat flow. We call it direct. This is a direct coefficient. This is also direct because we have a same symbol, but its small q is F small q contribute on JQ. Electrical potential gradient contribute on current density. So both these are direct coefficient, but this one and this one is in coupling coefficient because this is F capital Q contribute on current density. This is the electrical potential gradient. F small q contribute on heat flux, J capital Q. Okay, so this is an important description here. Every material have its own direct or coupling coefficient. Due to this, so that will lead even we apply the same driving force acting on your different materials, that will lead different flux. So this is why, because every material have its own direct and coupling coefficient. So here I'm going to introduce you L capital Q. What is L capital Q capital Q? Based on the definition is when I apply the 1 unit F capital Q, the change in heat flux we call the FL capital Q capital Q. And this is direct, as we mentioned, like you apply the unit temperature gradient, how much heat flux you induce, that will be correlated with thermal conductivity, kappa is thermal conductivity. But y equals to this, I will derive it in the following slide, but just give you a concept here. For regarding to L small q, which means that when you apply the 1 unit of F small q, then the change in current density, which also means that when you apply the connect to the battery, the same battery, the current in the current density you induce or passing through these materials, that will be related with what? If you connect different material to the same battery, the current won't be the same, right? Depending on the electrical conductivity though. So actually, dou equals to L small q, and kappa equals to L capital Q divided by T. So I'm going to show you why by using like 2 examples in following 2 slides. So the first one will be the thermal conductivity part. And besides like the deviation, I also want to give you some hint or give you some ideas how to measure the real intrinsic thermal conductivity of your materials. Okay, so let's move to the like direct coefficient, and here will be the L capital Q capital Q. What we have here is we have a question one, and we separate into small a and b, 2 different conditions. So let's read the questions first. What is the heat transport in a conductor with a temperature gradient? So first of all, you can draw like I have a conductor, and this conductor with a temperature gradient here show like this. So what is the heat transport? What is the J capital Q passing through these materials? So first thing come out from your mind is how many driving force or possible driving force exist in this system? How many? Just at least you can see one driving force, which is a temperature gradient, J capital Q, right? Oh, sorry, F capital Q, right? So you can use the flux force equation. Oh, sorry, you can use the yes, you can use the flux force equation here, because the question is what's a J capital Q? J capital Q, so only one driving force, you have L capital Q and F capital Q. So because only one driving force, so this is alpha equals to Q. Q and only F capital Q times L capital Q small q, or L capital Q, because it's F capital Q acting on JQ. And F capital Q is a negative temperature gradient divided by T. So we can write like this, show like this. Heat flux equals to this. And based on next will be, because as long as I know this value, then I can answer what's a heat flux, right? But based on Fourier's law, we know that heat flux equals to negative thermal conductivity times the temperature gradient. So the answer for this the heat flux equals to negative thermal conductivity times temperature gradient. But based on these questions, we know that we know what? We know the relationship between the thermal conductivity and L capital Q capital Q. So thermal conductivity kappa equals to L capital Q divided by T. So this direct coefficient equals to kappa T. Okay. So the real answer is negative thermal conductivity times temperature gradient. But this results also can show you what is the L capital Q is kappa T. As we estimation or we think right in previous slide, we think that thermal conductivity, the L capital Q for sure has some relationship with thermal conductivity because when you're acting 1 unit of temperature gradient, the heat flux you induce or how much heat flux you induce will be related with thermal conductivity of these materials. So this is we get the direct coefficient. And the second, the B, small b, actually is what is a heat transfer? Also asks you about J capital Q in a conductor when it connect in series to a Hoffman voltameter, and there's a temperature difference across. So it turns out we do also have a temperature gradient across these materials, but besides that, this material also connect in series or with or to a Hoffman voltameter. Hoffman voltameter, what is a Hoffman voltameter? It shows like this. People usually use this Hoffman voltameter to electrolyze water. Water is here, so we connect with a power supply, so we electrolyte the water. This is DC power supply. Then it apply across these two electrolytes, and we will producing oxygen at the anode and hydrogen at the cathode, and which is collect. You can collect both gas from these two tubes. Then in the external circuit, we have this metal with temperature connect with a temperature gradient because in series with, right? Okay, so the same current will be passing through this your interesting conductors. So how many driving force acting on your interesting conductor will be have probably one driving force for sure a temperature gradient. The other one would be probably will be the electrical potential gradient. But due to this equipment, this is some kind of electrolyte equipment. The temperature gradient will lead the heat flux. The electrical potential gradient probably will lead the current passing through. But due to consider with this equipment, I will assume that the resistance is quite large. That probably will lead the current passing through my interesting conductor is approach to zero. But they do have the electrical potential gradient, but just due to the resistance is quite large, so the current probably will be close to zero. So based on this idea, I will try to write down because we have two driving force, right? We have temperature gradient and also the electrical potential gradient. So uh, um, two driving force. So you need to write down the relationship for the two flux. So the heat flux directly driven by F capital Q and coefficient will be capital Q contribute on JQ. And the other we have a small F small q is the electrical potential gradient and contribute on heat flux will be small q capital Q. And the other you need to write down is current density directly driven by F small q. So we have a QQ. And the other driving force is F capital Q. So we have F capital Q contribute on small q. So we write these two equations as long as you know you have two driving force. For sure, you need to write down the relationship between the flux and two driving force. As long as we have this one, the question is, what's the heat flux, right? Heat transport. So now the information you have here is we know the JQ equals to 0. And this is 0, so I can have the relationship between the F small q and F capital Q. This 0, so I can just put this to right-handed side and divide it L small q, I will get this one. And also I know the F small q is negative electrical potential gradient. So based on this, I need to substitute F small q in terms of F capital Q to allow like I can put them together because both have the F capital Q. So this is what we deal with. L capital Q, we take the F capital Q outside. This is substitute here, so we have this times this divided by this, and this negative, and we take the F capital Q outside. And also, as you know, what's the F capital Q is a negative temperature gradient divided by T. So we put it here, and the T put it back into inside. So we got this. And negative, this minus this, and times the temperature gradient. And this can be the answers because like X about what's the heat transport, right? But some people probably will write that down because the heat flux always obey the Fourier's law, so negative thermal conductivity prime times temperature gradient. So compare this, we know that the thermal conductivity K prime equals to this. So from here, probably you already get you can answer the heat transport. What is a heat transport here? But furthermore, if you think deeper, you probably will say heat flux always obey the Fourier's law. So you will write down negative thermal conductivity times temperature gradient. But you compare here, I find that the thermal conductivity here equals to this is the kappa minus the extra term. And this term, let me check, is positive or negative. L small q, actually, it will be the electrical conductivity will be positive. These two terms are based on the Osaka symmetry. The value are the same. So these are positive as well. So you kappa minus an extra positive term. So you will get the K, so the kappa prime will be smaller than kappa, which means that if you use this kind of equipment setting to measure the thermal conductivity of your materials, then you are going to get the kappa prime, which will be smaller than it is because it will be kappa minus a positive term. And this term is coming from, you have the coupling coefficient, something like that, divided by the direct coefficient and temperature. So let's also tell you that if you want to really get your thermal you want to do the thermal conductivity measurement, you need to make sure there's only one driving force, which is temperature gradient, acting on your materials. Otherwise, the thermal conductivity you measure, otherwise you are going to underestimate your thermal conductivity. And how much it lower will be depending on the coupling term. This times this divided by temperature and also the electrical conductivity. 所以这就蛮重要，就是告诉大家说，除了回答问题都是问热流的话，很重要的话，最主要是要顺便用这样的例子告诉大家说，我们刚刚求得的这个 direct coefficient L capital Q capital Q，我们刚刚觉得它应该跟 thermal conductivity kappa 有关，主要是因为它的定义，因为它的定义是，当我给它一个单位的 F capital Q，一个单位的温差的时候，然后产生对热流的变化，热流的变化会多少？那这个你就会直觉觉得这跟 kappa 有关。那的确推导出来之后，它就是 kappa T。还会跟环境温度有关，然后除了跟自己这个材料的 thermal conductivity 有关之外，然后第二个例子主要是因为这个只有一个 driving force，那我想，就是给大家一个参考。那下一个例子就会是因为我们这一节讨论到是两个 driving force，所以就会设定一个环境是有两个 driving force 的，然后一样问大家热流，然后先想给大家看说，其实热流就不会是直接是你当初想的那样，它还会第二个例，因为在我连接这个 voltmeter 它有电位差的情况之下，它也会对你的热流有所影响。那有时候，那它会有影响。那我想大家都看到它的影响的概念。但另外一个点就是说，如果你是用这样，你没有注意到你在量 thermal conductivity 的时候，其实你系统有其他作用力的时候，你就很容易低估你这个材料的 thermal conductivity。那另外一个就是大家对于就是我为什么这样推导的时候，可能会有一些不知道老说什么当初这样想。那我可以简单说，就是对我来讲，如果我有发觉我有两个力的时候，我一定会写出就是两个 flux，因为他们就是会互相，除了被他自己主要的 driving force drive 之外，它还有 coupling term。然后问题是问这个嘛？可是你想一下这个问题，如果你直接写这个，就没办法，因为他们两个没有东西可以合并，就他们各自是热流跟电位差，然后他们是direct coefficient 跟 coupling，就他没有办法变成一个化简成一个是，他们就是独立的。那如果你又不知道它各自是什么的时候，所以你就没办法给一个回答这个答案是 why is a heat transport，它答案就不会是这样嘛。对，所以我才会想到说，那我是不是可以用另外一个条件来让 F，我的那通常下一个想法就会是说，我的这个热流有没有办法被 FQ 所表示，或 F small q 可不可以表示成热流相关的函数？所以我才会就是用这个就是这个关系to get this relationship to replace 了 F small q in terms of F capital Q，那这样的话你就可以把它们化简，就可以变成这样子的值。对，那后面这个主要是另外带出提醒大家，就是的一些实验上面在量测 thermal conductivity 的一些想法，这样子。好，那接下来，因为刚刚我们回去，刚刚就是这个，我们已经秀给大家看，L capital Q capital Q equals to kappa T。那 electrical conductivity rho 事实上就等于 L small q small q。So I'm going to use the next slide to prove that is right. Also give you some like suggestions for want to measure the electrical conductivity of your interesting materials. Okay, so what we have here is we have a metal connect to a battery. Oh, battery is a F small q. You can write it here, F small q. What would be the expression of JQ and J capital Q? So you say, so they want you to write down the J small q and J capital Q. Describe how the apparent electrical conductivity law of a conductor changes in different two conditions. The first one is isothermal, and the second one is a diabatic condition. So isothermal is quite directly right. Isothermal means we don't have an temperature gradient inside our materials, so we don't. The F capital Q equals to 0. So which means that you only have one driving force on your materials, acting on your materials. So this is quite easy. And that driving force would be just directly the battery is F small q. But the other is a diabatic condition. What this means, a diabatic condition based on the thermodynamics, it will be tell you that J capital Q equals to 0. So you do have two driving force, but heat flux equals to 0 for question B, right? So easy one is isothermal, so I try to deal with this one. Even though I know it only have one driving force, one flux, but because your question is like you need to write down the JQ and J small q and capital Q, so I still write them down. J capital Q directly driven by F capital Q, L capital Q capital Q, and this is F small q. So L small q acting on JQ. Same idea, right? And current density directly driven by F small q negative electrical potential gradient, and we have a small q, F small q acting on J small q, LQQ. And this is the F capital Q. And we have the F capital Q acting on J small q. So I just use the flux force equation to write them together. And as based on the information I have, temperature gradient equals to 0. So that will be easy. What we have is the answer will be here. And because this is the answer, but if you want more, I will say based on the Ohm's law, we know that the current density equals to negative electrical conductivity times the electrical potential gradient. So here we know that L small q equals to electrical conductivity. So this is like think deeper, think more. So you can, based on this example, I can get this additional information for you. But for answer, actually, is this and this. And also, that's probably this will be better with low electrical potential gradient. For the question B, is a diabatic condition. Also need to write down J capital Q and J small q. So as I just write them down. Then, this is equals to 0, so this is 0, right? It's easy. But how to get this one? Because we have quite different terms, electrical potential gradient, temperature gradient. As I mentioned before, either you express this in terms of temperature gradient or use this in terms of electrical potential gradient. Then you can combine them together. So the hint here would be you use this equation. Then you can substitute the temperature gradient term in terms of the electrical potential gradient here. Oh, sorry, it's here. Then you take the electrical potential gradient, negative electrical potential gradient outside. I have LQQ minus this term, this minus this term. So I got this times this divided by this. And based on Ohm's law, you also okay. So before the question actually is J small q and J capital Q, right? So you can either stop here. But if you also think more, so this current density, this equation also need to obey the Ohm's law, so negative low prong electrical potential gradient. But I use a prong instead of the here because obvious the value is quite different. This is low, right? Low minus an extra term. So I got the low prong equals to low minus extra term. And this term, this is kappa T, positive. And as I mentioned, based on Ansaka symmetry, they are the same. So you have this term square. So for sure it's positive. So low prong equals to electrical conductivity minus the extra term. So for sure would be smaller than electrical conductivity. It is negative electrical conductivity. So what does it tell you? They'll tell you that if there's other driving force exist in this material system, then you use this system to have your electrical conductivity. You are going to underestimate its electrical conductivity will become your electrical conductivity minus an extra term. This term will be correlated with coupling coefficient and kappa T. Okay, so also just tell you that as long as you want to measure the electrical conductivity correctly, please make sure only one driving force, which is the electrical potential gradient, acting on your material. If there exists other driving force, for example, like temperature gradient or others, that will affect the accuracy of your electroconductivity measurement. So electroconductivity measurement must be performed isothermally. Okay, so this is some kind of quite important suggestions for measurement. Question 3 just tell you how to calculate the sigma dot, which is the entropy production rate per volume, or rate of entropy production per volume. So what we have here is we have question 3. The temperature gradient is observed on a heat conductive materials in steady state, which means that we do have a heat conductor material, and we have a temperature gradient acting on these materials and is in steady state. So under this kind of situation, what is the sigma dot? So based on what you learn here, you can use these equations to get the sigma dot, no matter there are one or more driving force acting on these materials. But here, we found that probably just one driving force, temperature gradient, acting on this material. So I can directly use the J capital Q and F capital Q because alpha just one, so alpha equals to capital Q. So I can get the absolute temperature times sigma dot E equals to the factors heat flux times the temperature gradient divided by T. And this is, we have temperature gradient divided by T. But here, we need to know the sigma dot. So here you need to figure out what's the heat flux. What's the magnitude for heat flux? So based on the Fourier's law, you know that equals to negative thermal conductivity kappa times temperature gradient. So we use this term to substitute J capital Q. So we will have the less 10 2 times less 10. So we got the negative negative. So we have positive kappa temperature gradient squared divided by T. Positive positive positive. So this value for sure would be positive. And sigma dot, so you need to move to here to the bottom. So this is the results for the sigma dot. But by the way, I just want to highlight because some student asked me before regarding to the unit for the kappa thermal conductivity. So do you remember what's the thermal conductivity? This kappa, the unit for here is watts per meter K. This is the temperature. So we have a watts per mini K. And watts can be rewritten as a joule per second. So we have a joule per second. And at the bottom, we have so this actually is here, meter K. And this is a thermal conductivity, right? If you times the temperature gradient, the unit here would be the K divided by the meter. So, sorry. So you can delete the K here, and we got the joule per second area per area. So this is the flux for heat flow. So just double check for the unit. Okay. And the other, the other question would be if there's a concentration difference observed on your interesting material, of probably is the case we mentioned before. For example, like this case we mentioned before, we do have a concentration variations along these materials, and composition A here, XA1 is larger than XA2 under these situations. And as long as the system reach like a steady state, then what's the sigma dot? Based on the um, the questions, first of all, you need to find out how many driving force acting on these materials. Based on the description, probably just one driving force, which is the chemical potential gradient. So just write it down, flux Ji times the Fi, small I. So here the F small I is a negative chemical potential gradient, and atomic flux can be rewritten as a negative mobility, concentration, and driving force based on the fixed first law. So then we find just term this, so we get a square term. So this is also larger than zero. But regarding to the sigma dot, you need to move the temperature divided by temperature at the bottom. So that will be the results. Okay, so this is just for your reference. So we already finish this part to show you how to estimate the sigma dot for these two cases. But here we just introduce the driving force on just only one driving force acting on your materials, either temperature gradient or concentration gradient. But following case, we are going to introduce you some spatial or interesting conditions with two driving force is we call the Seebeck and Peltier coefficient. Um, but before we move to here, just give you a quick summary for what you have done or what you have learned here. Don't forget, every material have its own direct and coupling coefficient, which also means that the coefficient, no matter it's directly or coupling coefficient, is related with material's property. Okay, not just the complicated coefficient. This coefficient actually is equals to is a dependence with materials property. And after series deviation, we find that the L capital Q is kappa T is proportional with thermal conductivity. And L small q, which is the direct coefficient, is equals to electrical conductivity. But we also highlight or label under what kind of conditions we can measure it correctly. For example, like in order to measure the material's native or intrinsic thermal conductivity, you only need to make sure there's only one driving force, which is temperature gradient acting on your materials, then with no electrical field, concentration gradient, and so on. To measure the intrinsic or native electrical conductivity of your intrinsic materials, um, isothermal conditions is necessary. For the same idea, there shouldn't have the electrical field or other parameters difference serving as a driving force. Then that can help you to measure the real electrical conductivity of your interesting materials.